Okay, yes, and thanks for inviting me. That was the right time to say that. I should say first, I am recording. I had a vague idea, if this goes well, to put it on my YouTube channel and make it public. If anyone is not okay with that, now is the right time to tell me. It's fine if you're not. Like, if anyone's not okay with this, this is completely fine, but you have to tell me. If no one complains, then I might or might not put it on YouTube. This kind of goes against the idea of being interactive like a classroom environment. It's like, yeah, I want you to talk and interrupt me, but then you're also being recorded for the world to see. So these things clash with each other. I'm not quite sure how to square the circle there. You can also write in chat, I guess. I probably will, if I keep chat open, then I'll see it if you want to use that.
Also a suggestion, Jules. So also if people are more free to ask a little bit after, your talk. So then, you have the two kinds of questions, clarifying questions right now and then,
Yeah. Or we can also do a thing where like I cut the recording at some point, and that's like, so I mean, this beginning part will not be on the recording. I'll cut it after here and then before some question time at the end, but you can also interrupt me anytime you like in the middle. This will not be derailing me because for reasons of being very busy, I didn't really have any time to plan this adequately in any way. So I'm basically improvising. My plan is to talk about the theory side, and then at some point just completely context switch to talking about the implementation and basically show you a tool demo to show you what this thing looks like in practice. Okay. Okay, everything should be charged. So now I want to share screen from this, share whiteboard. Now I should be able to go like this, and yeah, okay. Okay, but so before just launching into some random theory, I guess I should talk about the big picture. I guess I can talk about the big picture while there's a big white square facing you. I guess I have enough time to kind of take it slow and talk about the history a little bit and kind of how these things fit together. So I am not an economist, as you probably know. I am half of a theoretical computer scientist and half of a mathematician. And these are two subjects that have quite a big overlap. So there's quite a lot of people like me that have one foot in both of these two subjects. I started out doing game theory from the computer science and mathematical logic perspective, and that's a kind of well-known thing. Lots of computer scientists do some form of game theory for various different reasons. And then I met a guy called Victor Vinchel, who's this kind of crazy maverick macroeconomist. Like officially, he's doing like econometrics and some currency theory stuff, but on the side doing like cool kinds of crazy out there visionary stuff. And in the end, he left academia and now he runs a startup. It's a funny situation. But then I also met Philip, who at the time was Philip Sun, who at the time was his postdoc in Mannheim. So Open Games were born in Mannheim while I was visiting them for 3 months. So Open Games are this weird thing where they're very mathematically technical, and it's really kind of drilling down into the kind of deep foundation, the mathematical structural foundations of game theory itself. So getting kind of far away from applied stuff. But it was always the intention to basically be practical. Like this is like doing theory in order to do practical stuff better later. It was never supposed to be an exercise in just exploring the foundations of game theory. And this eventually now is happening in the last year or so. Practical things are beginning to actually seriously happen. We're not to the point where we're writing down papers quite yet. But there was a large delay, and probably the biggest reason for the delay was that adding probability to open games turned out to be outrageously difficult, significantly more difficult than I thought at first. And that's the Bayesian open games paper. Like the second 2/3 of this is all of the and this was like, this makes my head hurt, the theory in that paper. But then it turns out that this theory can be mapped by another outrageous coincidence. This happens to map perfectly onto the programming language Haskell, so that basically all the theory is handled by the programming language's type system. And then you can just do practical stuff with it. And somehow it just works. So in the second half, and I don't have a planned time, but I guess I'm planning to spend about 2 hours-ish in total, probably, and probably about an hour on theory and about an hour on tool demo, I guess, which is probably not quite as much time as either of them need individually, but yeah, I want to talk about too many things, I guess. Okay. Okay. Now, what open games are is a completely out of the blue reformulation of game theory. Like you have normal form and extensive form, and everybody understands them. And then open games are just something from outer space. They look totally different. And the claim is not that this is better. This is not in every situation. I'm not claiming that this is how game theory should always be done. You in order to gain the benefits of, the thing that you want to gain is compositionality. Compositionality is the thing that everything should factor through. So compositionality is all about, you build pieces of the things that you care about so that basically you can hide the details of their implementation or their behavior in a box and put an interface around it. And then you can kind of forget what's in the box and just deal with the interface. And this is entirely how software engineering works. So software engineering is all about, in fact, all of the whole of how computers work, how the internet works, all these kind of technologies. To some extent, also kind of mechanical engineering is also all about this. You have a lot of detail inside something, but then you systematically forget the details and you just remember the interface. And this is not a silver bullet, it's a methodology, because of course picking good interfaces becomes a serious art form. Your interface needs to carry enough information to do what you need, while not so much that you're overloaded with information. So open games are supposed to be the compositional equivalent of games. So they're things where you can forget the details and kind of hide them behind this interface. And then the interface, you would have seen in the paper that the interface is these 4 ports where like the initial state comes in, some stuff happens, and the stuff includes like rational players jointly optimizing, doing Nash Equilibrium stuff. And then some, I'm reversed on camera, aren't I? Some state comes in, some stuff happens, and then some new state comes out, and that thing gets propagated forwards to whatever's happening in the future. And then some stuff happens in the future, and then you get some payoffs coming back. And you need these payoffs because when the stuff happened going forwards, these were choices made by players who are optimizing the future value that is coming back here. But then they need to hold up their end of the bargain because there could be people behind them in the past and they need to pass back their payoffs. And that's, so this is the mysterious part. The fourth leg of an open game, which is, I normally label S, is the one that is just very mysterious. But it's all about a kind of reversal of perspective, because in a compositional formulation, everything is sort of on an equal footing. So a player becomes the same kind of thing as a payoff function. So you can kind of switch your perspective between them. So a player essentially consumes payoff in the sense that the payoff is an input to their objective function. Yeah. No, the payoff is the result of their objective function. It's the input to their optimization procedure. But you can flip perspective and you can also put yourself in the perspective of the payoff function, and now you have to produce this for somebody else. So this is really the best explanation I can have of this kind of mysterious shape that these interfaces have. Okay, so this is becoming a little bit meandering, as is inevitable when I have no slides and I'm just freely talking. So I guess I need to talk about monoidal categories, basically. So, what monoidal categories are, so this is the foundation that everything is built on. You take a monoidal category of functions of some kind, either ordinary deterministic functions or stochastic functions or some other kind of functions as your baseline, and then on top of this you erect another category that has like another monoidal category, and this now is your category of games. So I need to talk about what these things are, and what they are is a sort of axiomatic process theory. Yeah.
So before you get into this with technical part, so in your analogy where you talk about software engineer, like there's a difference between obviously when we talk about game theory, because in software engineer, like we have an input and output, right? And those things can interact but independently. But when we talk about game theory, it's the players consider they have beliefs, they act strategically.
Yes. The information flow, the information flow is much more complex than you get in a computer program.
Exactly. So
yes,
my question is there how this is the mysterious part you're referring, and
yes, and in fact, I mean, this is really the reason that the definition of open games is so hard to understand, is that it's trying to account for this two-directional information flow that you have. Kind of, I explain it like facts go forwards, factual things go forwards, counterfactual things go backwards, or rather, more accurately, agents reason counterfactually forwards against a backwards arrow. Okay.
Just another quick question. I would like to know if you can elaborate on the question. I mean, on the following. I've read that one importance of compositional game theory is that they can help to build large and more complex game.
Yeah.
Based on smaller ones. So can you basically explain that one?
Yeah, at least this is the idea. I mean, I will come to this. I think this is something I should wait and come back to later. I mean, this is essentially the most important point. And this is something that's true in theory, and finding out the extent to which it's true in practice is kind of my main thing at the moment. Like, to what extent can you actually in practice build complex games from simple ones? But yeah, I'll come to this, and I'll show it. I probably want to show this kind of thing also in the software.
Okay.
Actually, doing these calculations on paper is just a nightmare.
All right.
So a monoidal category is a sort of axiomatic process theory. So it's a monoidal category is like a class of processes. So for example, there is a monoidal category of ordinary deterministic functions. There is a different monoidal category of linear functions, or equivalently matrices. There is another monoidal category of stochastic functions. And I mean, one of the reasons that monoidal categories are such a useful abstraction is that they're extremely common. There is a lot of them. A lot of kind of familiar things turn out to fit this pattern. And then open games turn out to be another one. So open games form another one of these things, but it's a much more complicated one. A monoidal category is a thing where you have essentially processes where you can combine them in two different ways. One is you can combine them in sequence, so you can do first one, then the other. And then the other one is you can combine them in parallel. And we draw a process typically as a box like this. So these are called string diagrams. So here F is a process, and these X and Y, this is the other data that your category needs to carry around. These are like types. So this just says that F has, I'm about to say input and output. F has input type X and output type Y, except that's not always accurate, and sometimes you have to be careful throwing around words like input and output. So it's much more precise to say basically a left boundary and a right boundary, and then it's much more agnostic to what the information flow is. So one of the things that you can do, if you have an F and then you have another process G, and G has to have a matching type that it goes, if F has right boundary like Y and G has left boundary Y and right boundary Z, then you can sequence these together and you can get a composite process with left boundary X and right boundary Z, and then the Y kind of disappears into the internals. So you can essentially put a box around this and you can call this FG and then kind of forget what's inside. So for example, so X, Y, and Z could be sets, and F and G could be functions between those sets. So F is an actual, like, honest to God function from X to Y. G is a function from Y to Z. Then you have FG is like G compose F. The thing, you know what I mean, it's function composition. It's the thing which on the input X does G of F of X. So that's one example, but there are many other examples. So obviously various classes of functions, as long as they're closed under composition, form this pattern. So like linear functions, smooth functions, stochastic functions, whatever, like any kinds of constraints or extra decorating data you can add on your functions, as long as it's closed under composition, you can make a category. So this much data is just, this is called a category. This is what a category is. So it's things where you can compose in sequence. And then another interesting example that is maybe a tiny bit less obvious, that's an example, but it still is X, Y, and Z are natural numbers, and F and G are matrices, and then your composition operation is matrix multiplication.
Sorry, can Y be functions? Can the element in Y be functions?
In general, yes. You don't care. They're just, it's a set of some stuff.
Okay, thanks.
So in general, yes, it could be. Occasionally that's important. And you can also, you can make weird examples as well, but I won't focus on the weird examples yet. And then this has to satisfy a rule like if you have three things and then you compose them in two different ways, these things must agree. This is a condition that it must satisfy in order that you're allowed to call it a category. So all of the examples I said satisfy this associativity law. So what that means is that, so the upshot of this is that I can just draw the diagram like this. I can just arrange beads on a string, and this notation becomes unambiguous. So it doesn't matter if I cut this thing here or in the other place, I get the same result. Okay, so that much is called a category, and then a monoidal category adds to this another operation. There must be a quicker way to erase everything on the page than just dragging my pen around until I've hit everything. So a monoidal category has another operation that says you can do two things in parallel. And now there's no constraints on the type matching because I just put them side by side and the boundaries grow together. I can put this in a box, and then this I write as F tensor G typically, and then the stacking operation on the boundaries is also written with the tensor. So this goes like X tensor X prime and Y tensor Y prime. So for example, I could have, so my I could have functions on sets, and my tensor could be Cartesian product. So if I have a function from X to Y and a function from X prime to Y prime, then I can make a function F tensor G, which goes from X, the Cartesian product X times X prime. So the set of pairs where the first thing is an X and the second thing is an X prime, this goes to Y times Y prime. Namely, if I have the input little x prime, I send it to the pair f of x and g of x prime. Okay, so, and of course, many classes of functions with extra constraints satisfy this as well. Smooth functions, stochastic functions, you can do this kind of trick with all of them. There are other examples where instead of Cartesian product, you use disjoint union, and disjoint union leads to another bunch of important examples where if the input is either an x or an x prime, then you can output either a y or a y prime by basically splitting on which one you get. So if you get given an x, you apply f and then you have a y, or if you get given an x prime, then you apply g and then you have a y prime. That's just another example. The category of matrices has two different important tensors. One is the direct product and the other one is the tensor product. This thing is actually named after the tensor product of matrices. Now a very, very important example for me is stochastic processes, because there the tensor product describes essentially joint distributions. So my preferred way to talk about stochastic, I've been abusing terminology. I guess I've been saying stochastic functions, which is fine, like functions that also have a dependence on a random variable. Sometimes I slip and call these stochastic processes, which is incorrect, because stochastic process means something specific. So I normally think of these as ordinary functions that input an element of a set and output a distribution on another set. This is, I mean, there are several equivalent ways of thinking about these things. So in general, these are just, these are functions from pairs of x and y to probability satisfying the condition that for every x, the total probability on the y's is exactly 1. I find it usually most helpful to think of them in this way, as functions that just ordinary functions, but they output a distribution. So dy is like the set of distributions on y. And then the Cartesian product of sets gives you a tensor product on the category of these things that makes it a monoidal category, where you have things like x times y, x times x prime to distributions on y times y prime. And the important thing is this, right? Distributions on a Cartesian product, these things are joint distributions. It says like for every pair you have a probability that pair is the thing that you have. So for example, you can marginalize. So from here you have maps to d of y and you have map to d of y prime. These are the taking marginals, but a joint distribution is not fully determined by its marginals. And actually, about half of the examples I've said have this magic property that they have an equivalent of marginals, and the equivalent of a joint state is determined by the marginals. So deterministic functions have this property that if you have a pair, then you know the pair if you know each thing individually. But in probability, that's not the case. For matrices, it is true for the direct product and false for the tensor product. So it's actually kind of useful to classify these examples according to this property. And this leads to basically all of the differences between the easy version of open games and the hard version in the paper that you read, is all of the places where we secretly use this fact that like a pair is determined by knowing both things individually. And this is once you start assuming this, it's like this fact gets everywhere. So once you lose it, you have to really do a lot of workarounds for this. Okay.
So I wanna get something clear, please.
Yeah.
So the distribution of y cross y prime is not equal to the distribution of y times the distribution of y prime, right?
Correct. Yes.
Okay.
Yeah. So that is, you have canonical functions in both directions, but they're not inverse of each other. This thing, if you round trip, if you start here and then you round trip, so you project out the two marginals and then recombine them, you've forgotten information because you've forgotten all of the cross terms essentially when you do that. Fun fact, this exact thing is also true in quantum theory, and a lot of this stuff was worked out by people doing quantum foundations. This is, it turns out that joint states in probability have quite a lot to do with entangled states in quantum mechanics. They're not exactly the same, but there's quite a deep analogy between them. And then quantum adds like one extra complication that I don't understand. Right. So, okay, and then, so I haven't finished entirely telling you what a monoidal category is, because I've given you some things and promised you that they're examples. there are some conditions that a monoidal category has to satisfy, but there's a very neat way to, so writing this definition down is actually really difficult. This is like an entire chapter in McLean's classic book on category theory. There's a really neat way to say it equivalently, where the equivalence is, I mean, the equivalence is also very hard to prove, but it's true, which is that they are precisely the things for which arbitrary diagrams like this can be unambiguously interpreted. I'm just drawing some random example. These things are string diagrams. So they're things where I have some processes, F, G, H, I, and then each of these things is going to be objects. I'm going to run out of letters very quickly. You get the idea. And what I can do is I imagine cutting this diagram like this, where, so for example, if this is in matrices, then, so if F, G, H, and I are matrices, then, and all of these blank wires are secretly the identity matrix of the appropriate size. And each of these horizontal cuts is, say, a tensor product. And then each of these vertical cuts is a matrix multiplication. It turns out that the answer that you get as from the algebraic expression from making these cuts, so this leads to like F tensor I tensor G or whatever, you get the idea. Like I can turn this diagram into an algebraic expression by cutting it. And this looks like it would be not unique because I have basically a lot of choice in the order I make these cuts, and also I can deform the diagram. I can kind of pull the diagram around. If I have this diagram, so I can cut it like this. So now I have tensor, tensor, identity matrix, composite multiplication. But I could also slide those past each other. I could push this way, and I could push this way. And all of the very complicated conditions that have to hold in order to be allowed to call something a monoidal category are exactly the ones that say that the result you get is independent of all these choices. So no matter how you pull the diagram around, no matter how you cut it, you're guaranteed the same answer. So what it means is that this kind of two-dimensional syntax is actually canonical. So these diagrams are like the natural syntax for talking about these things. Whereas the algebraic syntax, these are not canonical because there's a bunch of like, there's a bunch of equations between them. Like this thing ends up being equal to a bunch of other things that don't look the same. So that's sort of the big idea of monoidal categories. So it's essentially, it's twofold. One is that examples are so common, like there's lots of these things. And then the other is that the notation for working with them is so intuitive. Once you get past the barrier of proving these conditions, then you get this super intuitive graphical language. And the thing is that okay, I've been telling you the slightly technical version, but I think you can probably imagine that I could explain this to a non-math, like I could explain this to someone with no background in mathematics at all, and they'd probably pick it up. Like this thing is super intuitive. And this is, and aspects of these appear all over kind of science, all over engineering. There's probably a bunch of examples in economics, I guess, like any kinds of kind of flow diagrams of any kind look like this. And usually when you have diagrams like this, it's usually a sign there's a monoidal category hiding somewhere in the back, waiting to be discovered. Right. So, I mean, this is a lot of background. I kind of wanted to communicate the intuitive concept of what a monoidal category is. That's the thing that I wanted to do. I have sort of intentionally not left myself enough time to really explain deeply what open games are. And this is a thing I wasn't sure about. I could have tried to explain what open games are, and then I would not have had time to say anything else, basically. The way that I've chosen to do it, the story is basically, and then a miracle happens, and then you have open games. The definition of open games is pretty mysterious. Like it doesn't look like something that you should call a game. But everything is carefully arranged so that then you can start to draw diagrams where, and they're still string diagrams, where sequencing is sequential play. So first play this part and then play that part. And the tensor product is parallel play or simultaneous play. So this is very, very different to how extensive form does it, because in extensive form, you don't have what I would call true concurrency. You don't have truly simultaneous things. You kind of, if you have something that you want to say is simultaneous, you arbitrarily pick an order in the tree, and then you use information sets to express the fact that you don't know what state you're in. Monoidal categories are not like that. In monoidal categories, you have kind of true simultaneity. So this was one of my guiding principles all along. So this is something that comes from, this is kind of one of the big ideas of theoretical computer science. This comes from concurrency theory, process algebra, and actually game semantics, which is game semantics is a whole other thing, where they do sort of game-like things, but specialized to two-player zero-sum. And then they go into like crazy depth on the theory of two-player zero-sum games. This is a huge field. And one of the things they have there is true simultaneity. So I consider information sets to be a sort of artificial encoding of the thing that actually wants to be there, which is expressing the fact that things happen simultaneously. And simultaneous doesn't necessarily say anything about time. Simultaneity, in the sense I'm using it, is about causality. So I would consider these two. So I have a timeline. I have like past and future. So in that sense, on my timeline, G happens after F. But my laws of monoidal categories, if this thing is a monoidal category, I'm allowed to slide these things past each other and it's equivalent. Like this thing is forced to have the same, this is forced to be the same thing. So in this sense, being simultaneous is about causality. It says that F and G are kind of causally non-interacting. So that's one of the ideas that open games are built on, is taking this seriously. Also, monoidal categories are not the only way to do this. Theoretical computer scientists have other ways of doing this, but this is the one that I like. I like it because it relates to a bunch of other mathematics like matrix algebra and stuff. Okay, so yeah, and in the end, you can do stuff like we can have a process which is like the decision by player one in a game, and a process which is like player two in a game. And then I can have a process that's like a payoff function. And then I can wire these together. And okay, now previously I had all my wires were undirected, but now for reasons I have to start directing my arrows. So I have this. And this is okay because I could say so. I can label these wires by say the type of choices that these players can make, and then these wires are going to be labeled by say the type of real numbers. And the arrow, which is the other decoration on this wire, is actually part of the type secretly. So really, this is like an unlabeled thing where the label is the set of choices plus the fact that you're going forwards. So it's just like every wire is carrying around an extra bit of data that says if it's a forwards arrow or a backwards arrow. So in that sense, the direction is kind of a natural thing, and actually diagrams in matrix algebra end up doing the same thing, where backwards arrows are like a transposed matrix. Okay.
So the R here represent the payoff of player one, right?
Yeah, or rather, this is the set of all things that could conceivably be payoffs.
Oh.
So here, my payoff function is going to be a function from AB times CD to R times R, and then that's its type. And then in a specific example, I would have to pick a specific function. And then you can make any bimatrix game you like. Now, so U is a function. So each of these boxes is an open game. And now I'm drawing diagrams in this open games monoidal category. And each of these boxes represents a particular open game. And U is a particularly simple one because it's not a player. It's just a lifted payoff function. So U is simple, whereas P1 and P2 are quite complicated. They encode, so inside their definition, which really I don't really want to go into, but I can if there's demand for it. These things encode the fact that these are argmax players. So it's encoding the fact that you're doing game theory gets encoded kind of just inside these boxes rather than the structure, and not in the structure of open games themselves, if that makes sense. So we have the monoidal category of all open games, which is a vast over approximation of game theory. And then we have specific processes inside it, which are game theoretic. And then we can build games by just wiring together those processes and ignoring all of the crazy stuff outside. So this is not significantly different to if you have, say, sets and functions. Like if you're an economist, you have like some kind of reasonable sets and reasonable functions that you know probably have some economic meaning, and you're probably not going to reach for a set like a axiomatic set theory textbook and come up with like crazy examples of sets and functions that make the universe melt. You could, but you don't. Like you wouldn't be doing economics. So this is like this. We have this kind of big over approximation in the space of things we could do, and then we narrow down to things which are reasonable. So the fact that we're doing game theory enters late in the game.
Sorry, what if some player can set up rules for others? So his choice, it will be functions.
Okay, so I mean, you can ask a lot of technical questions like this.
Yeah, you can skip this question.
Yeah. So by default, things end up being actually really similar to classical game theory. What you get is that the structure of the game itself, so the contents of this diagram and the meaning of all these boxes, ends up behaving as common knowledge. And this wasn't something I planned. It just happened. It falls out of the mathematics that the structure of the game is common knowledge. Like, it's really hard. It's really hard to avoid this assumption, it turns out. I know why game theorists spent like half a century trying to get around this assumption. Dealing with, if we want to deal with, for example, incomplete information, we still have to do the Hassani trickery. Just the same. That doesn't change.
Yeah, there's a question about this. So can open games deal with common knowledge? It's like a very basic assumption of Nash equilibrium.
Yeah, so open games assume common knowledge by default.
Okay.
Situations without common knowledge get equally as difficult as they get in ordinary game theory.
Okay, thank you.
Which is to say, kind of, you can handle it, but you have to do tricks, and they're basically the same tricks. We do Hassani type spaces in open games. Okay, that was actually one of the main motivations for Bayesian open games in the first place.
Yeah. So I guess in this example, player 1 and player 2 are choosing are playing simultaneously, right?
Yes. Yeah.
So how will be the graph if the play are sequential, like player 1 plays and then the player 1 plays and then player 2 plays?
Yeah. So this is a good question. So, and it's like, I wonder, can I do this? So if I was sufficiently set up with the technology, I could show off and I could kind of modify this picture live, but I think I'm not set up for that. So I'll just do it again. So now let's say I want player 2 to observe what player 1 does. So the first thing I can do is I can deform the game like this. Okay, so this is equivalent. So this gives you the same result. I've just deformed the diagram a bit. I've now I've decided that player 1 happens first, player 2 happens second. So now this one looks like an extensive form game with with information sets. So the information sets are expressing the fact that at this point, player 2 does not know the value here, even though it exists. So there is a value here, but player 2 can't access it because there's an air gap in the diagram. There's no causal link. So what I can do is now to modify this to be a sequential game. What I have to do is I have to pull off a copy. So I can add a copy function here, and I can pull off a copy of this move. So now this is causally linking player 2 to player 1's decision. So now you're starting to see compositionality. I mean, this is like the most basic demonstration of compositionality I can possibly make, but I've taken an existing game and then I've made a kind of local change to it in order to now express something different. And there is a natural third step in this story, which is, let's say player 2, let's say we have we have an intermediate situation where player 2 isn't completely ignorant of what player 1 did, but also doesn't observe it perfectly. Let's say player 2 observes some function of it. So I can just stick a function here. So I can stick that function on this wire, and now so if player one's choosing an X, so if player one's choosing an X, then previously player two was observing an X, but now this F might be some F prime, X prime. So F is just some function from X to X prime. And this works for any function. But actually, how you relate this back to extensive form is you think of X prime as being the class of information sets and F as being the projection onto that quotient. So you have X prime is X modulo the equivalence relation, the information equivalence relation, and then F is the projection from X onto the quotient, which just says for every element of X, you just say what equivalence class is it in.
So the F here is like the belief, because if player two cannot observe what player one has played, then he form a belief of what he might.
Yes.
Play.
Yeah. So in the deterministic case for pure open games with pure strategies, this is not especially interesting. But in Bayesian games, this is a very interesting situation, because then in Bayesian open games, so what we get from Bayesian open games, and I always find this terminology confusing. We get, sometimes it's called Bayesian Nash and sometimes it's called weak Bayesian Nash. It's the version of Bayesian Nash that doesn't involve explicit beliefs. Explicit beliefs are actually, we don't know how to deal with them yet. So we get a situation where player two has a correct prior about player one's strategy. So basically we only have the situation of correct priors. Which is to say, everybody knows a priori everybody else's behavioral strategy. And then, so player two has a correct belief about the strategy player one will play, which is going to be some distribution on X. And then what player two observes is F of X. So player one will play this mixed strategy, and then it will be, essentially you will draw from that distribution. So you'll get an actual X. And player two will observe F of X. And then they will then Bayesian update their prior, and they'll get a posterior on the value. So, and player two's reasoning goes sort of here like this. In fact, not just there, but then they continue round to here. Because, so the thing that player two cares about is their expected payoff. That's the thing that they're optimizing. So what they need to do is take their observation. They need to use their observation to update their prior on what player one is going to do. So get a posterior here. And then using the posterior here, they can get a posterior on their expected payoff for each choice they could make. And that's the thing that they optimize, the expectation of that.
I have a question.
Yeah.
So in the current setup, like I feel it's probably hard to solve if player two and player one, like one is Bayesian and the other is non-Bayesian, and each other don't know other's reasoning type.
So actually, I think we could do this, at least in theory, but I think I've never tried it, so I don't know what you'd actually get.
Yeah, like, but especially when the types are not common knowledge, and probably, yeah. I'm not sure, but maybe we could modify this a little bit.
Yeah. Sure. So, I mean, if you restrict player one to only be allowed to play pure strategies, then this situation kind of degenerates, because then, is that true? Yeah, then that's true, because player two's correct prior will just tell them what move, and there's nothing to learn. The other way around might be more interesting when player two is restricted to playing pure strategies. But then player two has to be a Bayesian agent. If player two is not a Bayesian agent, then this thing also degenerates. So yeah,
I feel like maybe two players here are kind of easier to deal with, but with a like big mixed communication structure.
Yeah.
I'm thinking of that. Yeah, probably could be really hard for people to learn the information flow.
Yeah.
Right.
Right. Okay.
Sorry. This red light is belief system, is it? Can I think of this?
Sorry.
The belief. This red circle.
Yeah.
How to draw higher order belief?
Higher order beliefs we do not know how to deal with.
Okay.
So, yeah. This is the thing that open games give you certain benefits, namely the benefits of compositionality, and we're still exploring how much benefit that actually is, but you pay for it. And you pay for it in things which are possible becoming very difficult, and other things becoming either impossible or at least we don't know how to deal with them.
Yeah, of course, but it's better than extensive. Extensive doesn't have the belief system.
Right. So the solution concept, which I guess I will call strong Bayesian Nash, the thing where you have kind of explicit higher order beliefs being carried around, we do not know how to handle. It might be possible, it might not be possible, we don't know. And then stronger things than that, like sequential equilibrium, are completely no idea. We believed that we essentially hit diminishing returns in playing with equilibrium refinements, where basically we got to a thing where like, you can do the Hassani trick to kind of finite belief hierarchies, and it's probably fine. Like it seems to be good enough for quite a lot of practical situations.
Have you put all this result down?
Right?
Have you put all this result down? I mean, is it a working paper?
Sort of and sort of not. I mean, the Bayesian Open Games paper does contain some of this stuff, but most of I think there's nothing written down where we actually use Hassani types explicitly, for example, but there will be in the next probably 6 months.
Okay, thanks.
So coming back, for example, in the case of a simultaneous game,
yeah,
what if the player wants to mix strategies, not only play pure strategies? How can we model that?
So this is okay. So the way that I deal with essentially normal form games and mixed strategies is by overkill, because if you just say everything is Bayesian, all your strategies are actually behavioral and all of your agents are actually Bayesian agents, it turns out that it just specializes to mixed strategies in the case where everything is fully simultaneous, because nobody ever learns anything, so no Bayesian updating ever happens. And this is, and I get away with this essentially because we have a computer implementation. So this is just like the computer wastes a bunch of time doing unnecessary calculations. To not overkill, to actually hit mixed strategies directly, turns out to be a bit tricky. I think we probably know how to do it, but it's a little bit tricky.
Yeah, that's even the question, like how to hit the mixed directly.
Yeah, I mean, we sort of can. There's a paper by a bunch of people who were at Strathclyde before I came here. Actually, I don't even know where you find this paper. Is sort of published, but I don't even know if you can find it on archive even. It's it's a paper that's kind of in theory exists, but nobody can find it. I don't even know if I have a copy, although I can just ask for one. This is the kind of, when I say you pay for it when you get compositionality, I'm not joking. Like, you lose some really basic stuff. Like, mixed strategies are probably possible, but they become like weirdly difficult. Min-max, like, no idea. Don't know how to do min-max. like Pareto, optimal strategies, no idea. Like these are things which are like, okay, yeah, we don't know how to do sequential equilibrium, but that's okay because sequential equilibrium is kind of difficult anyway. But we don't know how to do some really basic stuff like min-max. Somehow it wants to fit things which are sufficiently Nash-like, but then mixed strategy Nash is Nash, and we don't, like, that is weirdly difficult. It's very strange. I don't fully understand why some things are more difficult than others when you do it this way. There's a lot still to explore.
Question there quickly. So have you thought about correlated equilibrium?
Yeah, that's another thing so that's one which also falls out of weak Bayesian as a special case. So that's the one where observations are made, but observations not made of previous strategic choices, but only of just a random variable, a joint random variable, and then that specializes to the right thing. I think that's in the Bayesian Open Games paper, but it could be that it was cut out.
Yeah, I was asking because that one is very nice computationally, right? Because the system of linear equations. So I was wondering, if you thought any about that in terms of, using the linearity plus the compositionality.
Okay, yeah. This relates to something which I should talk about quite soon. So I should pivot to talking about the implementation. I have successfully not defined open games. I successfully told you about, I've done what I wanted. I've told you about monoidal categories, which is just a nice thing that I just like to talk about. And then I've hand-waved open games. But I haven't told you what this category is. It's the thing which is in this paper. And I can't explain it any better than we explained it in the paper, because if I could, it would be explained that well in the paper. Like the paper.
Everyone read the paper, so.
Sorry. Yeah. Right.
Everyone read the paper, so don't worry too much.
Yes, and if you didn't understand it in the paper, I don't have anything better. Like this thing is just hard to explain. So what I want to do is I want to stop sharing on this side. And I want to, I guess I'll keep the iPad at least connected to the call in case it comes back in questions. And then I want to share screen on this side. Okay. I'll just keep this on, I guess I'll keep this on the screen while I talk. So I've talked about the theory a bunch. So open games are like drilling down into the kind of theoretical, mathematical foundations of game theory. And we're talking about like formalizing the kind of causality that you get in game theory. Like, what does it mean to do counterfactual reasoning and this kind of thing. There's a completely other side of open games, which is the practical side. And so everything has to go through a computer implementation, because I know from several years of painful experience that doing any examples, even extremely basic ones, by hand on paper is just impractical. The kind of calculations you get into are just like, even a 2-player by matrix game is just like a nightmare of calculations. So everything has to go through a computer. That's just how it is. Now, the question is, what can you do with this computer implementation? And there's an important thing that the answer is not. The answer is not equilibrium search. Open games are not useful for equilibrium search. So this is not the thing that you would usually think when you see when you see game theory on a computer. Equilibrium search is obviously a very difficult and very important problem. The theory of open games doesn't help. It doesn't say anything about equilibrium search. You could try to do equilibrium search on top of open games. It might be possible. It might even help you in some way. It might even be helpful for the problem. I don't know. But a lot of the time you'll be fighting against the theory because you're doing something that it basically fundamentally doesn't want to do. What it wants to be is an equilibrium checker. It's a thing where you specify a game and then you specify a game and then you specify a strategy profile. And then it says, so the simplest thing is you give it a strategy profile and it says either yes, it's an equilibrium or no, it's not an equilibrium. And this sounds extremely underwhelming after you do all this crazy theory. Like you go away, you learn category theory and it takes a long time. And then all you get is an equilibrium checker. So in that sense, it seems like a big kind of anticlimax. Our kind of working hypothesis at the moment, and this is a thing that we're actively working on kind of exploring as a hypothesis, is that equilibrium checking is more useful than it sounds. So the first thing is that you can get a lot more information than either yes equilibrium or no not equilibrium. This thing can return a lot of detailed information about what happened during the course of the play. In that sense, it's a sort of simulation tool, but it's kind of a simulation tool that's also trying to be an equilibrium checker at the same time. So it's like as it plays, it's checking equilibrium, but of course checking equilibrium involves checking also all of the counterfactuals. So it means also checking all of the things that didn't happen, all of the things that are in the support of your strategies that happen with small probability, this kind of thing. The other thing you can do is that once you hit some critical scale, it seems that you can start to do kind of interesting economics on top of equilibrium checking, where if you have a bunch of parameters, you can basically you can loop over a bunch of parameters where each iteration of the loop is doing one equilibrium check, but you're actually like searching for various combinations of parameters that make the equilibrium check pass or fail in certain ways. So you can say something like, give me the minimum value of this parameter that causes this player to be in equilibrium for this strategy in this way. And once you hit some level of complexity, it seems you can start to do some kind of interesting economics with that. Okay, so the Open Game Engine, so this is all open source. This is all on GitHub. Here is the address. It's a fast-moving target. Things keep. I mean, you can kind of see yesterday, 10 days ago, last month. Like things are changing a bunch, and it's not quite in a. It's almost, but not quite in a kind of civilian usable state. So this thing has been around for like a year and a half, and for most of that, there were only 2 users, which is me and Philip Sun. This thing was very difficult to use. Its usability has improved a lot in the last month, mainly because we got some funding to pay a programmer, namely Andre, who is basically, so I'm a bad programmer. Like most of this was written by me, and I'm a bad programmer, so it kind of just holds together, just barely. Unfortunately, you still have to basically build this from source as Haskell. So you need to, like, if you never used Haskell before, which I would not expect, the overwhelming majority of economists have never even heard of Haskell. Like this is like an outer space language. If you're coming from MATLAB and Fortran. So, okay. So let me talk about this. So here's one I made earlier. So this is the preparation that I did. Is I made this file yesterday, and actually just to check that I understand the new syntax, because this syntax has only been enabled since about a week. So here's what prisoner's dilemma looks like. So this is just keeping Haskell happy with a bunch of imports. Here I say a prisoner's dilemma move is either cooperate or defect. So this is defining a new data type with 2 values. So this is like an enum type. This is keeping Haskell happy. And now I can write the payoff function. And so this is ordinary Haskell code. This is what writing a function in Haskell looks like. Except I've written it in a slightly unusual way to make it look more like mathematics. But in general, Haskell is designed to look as much like mathematics as possible. So this is very close to just writing a payoff matrix. Now, this thing, so this is the payoff function. This thing is specifying the game itself. This is not Haskell. This is a thing called a domain-specific language. So it's a sub-language which we've embedded into Haskell. This line begins it, this line terminates it. Everything between these is no longer Haskell, but it's something different. It's actually, this language has no name. This is just the open game language. And this corresponds to the string diagrams I was drawing. So each block in this is corresponding to one diagram element. Actually, that's not quite true because the payoff matrix has vanished. But I could have done this a different way. So actually, there's only two sets of lines here, whereas there were 3 in my bimatrix string diagram. There were 3 diagram elements, and the payoff function has kind of disappeared. But each of these is describing. So each of these has a bunch of fields, and operation is saying what this thing actually does. So what this is saying is that this is a decision by player 1 with the moves cooperate and defect. So you say the identity of the player and the action space, and this has to be a finite list. This you can ignore because this is saying the action space is allowed to depend on the current state, but there is no current state. So this is just making that go away. Same for this. And everything else is basically encoding the wiring. So this says that so in a string diagram, you have a wire that carries the choice of the player. And then if somebody needs to observe it, you need to physically connect that wire to the place it needs to go. I'm reversed again. We're going left to right here. So physically connect that wire to the place it needs to go. This language does it in a different style, namely that the choice made by player 1 is named as a variable. So this variable comes into existence when player 1 makes that choice. And then this variable can now be used by later players. And now this, so this thing here, this is the payoff function I wrote. And this is just the first projection. So it says just take the first one. But the interesting thing here is, so this contains move 1 and move 2 as variables. And the thing is that move 2, the variable, so this is player 2's choice, and this looks like it hasn't been created yet. So having spent so long focusing on the point of true simultaneity and how it's better than what extensive form does, now we're in a programming language, we have to introduce an arbitrary ordering again, because like we have to have lines, like we can't have 2 lines simultaneously. We need this line and then that line. So somehow you can never quite escape from this idea of kind of arbitrarily picking and ordering. Maybe it's not a coincidence that von Neumann was also one of the founding pioneers of computer science itself. Defined the CPU architecture. So this variable looks like it doesn't exist yet because it looks like it doesn't come into scope This is like referring to a variable before you've defined it. But the answer is that this is not an ordinary programming language, because in an ordinary programming language, things only go forwards. Like you have this, like lines happen top down, variables which come into scope only exist below the point where they're created. Whereas here you have a forwards part and a backwards part interacting. And it's the same structure that's encoded in the diagrams with the arrows. And these keywords, these actually are determining whether it's forwards or backwards. So the ones that say outputs, these are going forwards. The ones that say returns, these are going backwards. So the fact that move2 looks like it doesn't exist yet is fine, because returns is looking in the other direction for its variables. Now to show you, okay, and by the way, so we have two different syntaxes, and this is, we were talking about this literally this morning on a call. So we have at the moment two different syntaxes. This is the one that I like. This is the syntax which I've had in mind for a long time. So these are equivalent. These contain exactly the same. These specify the same game. This one has much longer lines. It puts all these things on lines together, and it doesn't use these keywords. It uses like positioning to determine the meaning. So this one is designed for basically for economists. This is designed for people who are not computer scientists or Haskell programmers. Whereas to a Haskell programmer, this is much more familiar. But then I also imagine that sufficiently expert users who are economists will eventually kind of graduate to this one, because it's just more information dense. Okay, now I can show you. So this is the source code. Now, if I go over to the interactive, okay, this is left over from this morning's call, actually. So this thing, so PD is prisoner's dilemma, obviously. Colon T is saying, give me the type. And hang on, this is I want to get rid of this, because this was just a thing I was playing with. Reloading. Okay, now this has changed. So how you read this, this part you can ignore, this part you can ignore. This is the type of strategy profiles. So this says, what information must you specify for your strategy profiles? And then these are these 4 lines. This is the same as the 4 ports in the string diagrams. So kind of generic open game has 4 legs, like in, out, in, out. These correspond to these 4 things here. So this is saying that these are all empty. And now what I can do is I can run equilibrium checks on this. So hopefully I've got this set up correctly. This might take me possibly a few times to get, yeah, this is right, okay. So what I can do is I can say, so an example of an equilibrium check is I can say equilibrium PD void. So every open game has a context, but a game that has no legs only has a trivial context. So void is the name of the trivial context. It says that there's nothing else around this diagram, only empty space. Now I have to specify a strategy profile, which needs a little bit of boilerplate code, which you can ignore, but then it ends up being certainly, so this is coming from a probability library that I'm using. So I say certainly effect, and then and hopefully I haven't messed this up. Yeah, okay. And so I get this output, and so this output is the good one. This says that I am an equilibrium. So what this thing returns is a list of failures of equilibrium, so a list of deviations. So when it's empty, that means you're in equilibrium. So if I change so that player 1 is playing, player 2 is playing cooperate, now this thing gives me output. So okay, this part is still this part hasn't been so heavily worked on as the front syntax. So this thing is still kind of hard to read. This thing hasn't been made user-friendly yet. But how you read this is saying you have a single deviation where player 2, this is the state they're in, which is no state. They have some unobservable state. So this is saying that player 1 has played defect, but player 2 doesn't know it. Their strategy, so this thing is listing a distribution. So this is cooperate with probability 1. They're getting a payoff of 0. And then their optimal move was to play defect, which would give them an optimal payoff of 1. And then I could also say uniform.
Can I add a question here?
Yeah.
So can this kind of equivalent check code to deal with the continual action? So
not directly. In order to, I mean, it's the same as basically doing anything continuous on a computer. You have to you have to discretize. And actually, so I'll show you a bit later. I'll switch to. I'm showing you the simplest possible like baby example. I'm going to switch to a scary example to show you what we can really do. And there we have continuous things, and I mean, we haven't got to the point of doing kind of proper numerical analysis like smart discretizations or something, but we do have discretized continuous action spaces.
Question, Jules? Yeah, so I'm not a specialist on this, but I just made a connection. So I was thinking of this reinforcement learning, right? So basically they make, these deep neural nets play, a video game or, Go. Yeah, so is there a way, for instance, to play this basically by trying different things and specifying a loss function that kind of specifies some deviations?
Basically, yes. I guess not everyone here was here when we were talking about this slightly before we started. Basically, yes, but this is like in the last weeks. This is stuff that Philip Zahn is doing and right now, and I've sort of seen what this looks like, but I'm not quite in a situation to talk knowledgeably about it yet. I will switch to talking a bit about the machine learning aspects a bit later. I want to switch to something. So this is pure game theory, and like an equilibrium checker for Prisoner's Dilemma is not very exciting, especially if you see how much machinery is involved in this. There's kind of a lot going on. So this syntax is being parsed so I didn't write any of this code. This is what the parser looks like. Some more. This one's not too long, but then it's compiled. This part. This is I wrote. This is one of the earliest parts that I wrote. And then there's a back end, and the back end. Now, here's the kind of truly scary stuff. In the Bayesian Open Games paper, there were these coend calculus expressions where we were drawing these kind of integrals. This is the Haskell code that corresponds to that. This is the integral in that sense over this variable z, which you know because it doesn't appear in the output. And stuff. And then this is where and it's probably better if I talk about, there's a slightly simpler version, which is, this one. Can I talk about this one? This is a better one to talk about. Yeah, this is the simplest version to talk about. This is not the one that I was actually just using, but it shows off the most important difficulties. So this corresponds to a bunch of stuff in the paper. This is a decision. So how do I read this? Here is a list. This is my action space, a list of moves. This is my strategy. These are behavioral strategies. This is a function from X to distributions on Y. So these things are behavioral strategies of choosing a Y, observing an X. So this thing ends up being the model of an agent, a decision by an agent who observes an X and chooses a Y, and they're a Bayesian optimizing agent. And then, so playing the strategy ends up being, so strategy actually looks like so we get the distribution from, so we take an observation, we apply it to the strategy, that gives us a distribution, then we sample from the distribution, and then we return the sample. And then equilibrium checking, this is complicated, and this is directly taken out of the Bayesian Open Games paper. So we have a context that looks like, so H and K. So H is a joint distribution on an observable state and an unobservable state. And then K is a payoff function that depends, an individual payoff function that depends on choices and also the unobservable state. And then we say, this is an equilibrium if, and only if, for everything in the support of the states I could be in. Let me see, how's this working? Yeah, right, okay, so for every, so X ends up being, yeah, the information flow in this code is kind of hard to see. So this is actually looping. So X is looping over the support of this distribution. So this is looping over all of the observable states that could happen with non-zero probability. Then for each of these, you get a payoff function where you Bayesian update your prior with your observation, and then you use this as the, so this now is the posterior, and then this ends up being the posterior, then goes to your payoff function where it's combined. So then Y is your choice. So then this ends up being a function of choices. And then this is the thing that you maximize. Yeah, there's a lot going on in this definition. And then the version we actually use is like an even more complicated version of this for complicated reasons that does some other stuff as well. So this is the version that I was actually using. But at the heart of it, there's something very similar, that there's a kind of Bayesian update, and then you sample it, and then you use that as the parameter of the payoff function. Okay, so all of that was trying to show off that this is like ridiculous, absurd overkill for Prisoner's Dilemma. This is, I call this nuking a mosquito, which is exactly what it sounds like throwing all of this crazy theory at a kind of trivial problem. Here's an example. This is just from one of my modeling calls. I'm not going to talk about what this actually is, but this is a much more non-trivial model. So here's the name of the thing, and then these are exogenous parameters. So this was the point where I decided I'm allowed to call myself an economist now, because I have this many parameters. This is an integer, the number of players. Everything else is a double. So there's like 10 parameters of type double here. And then I'm not going to explain this. This is now giving you an idea of the kind of level of complexity we are at right now. This contains a bunch of hierarchical composition because, for example, so this first line, so this thing is actually an n-player simultaneous game where it's referring to a whole so this is an operator which is building simultaneous games from a list of games. So it's saying, give me a list, given a list of games, give me the game that says I play them all simultaneously. And it is the list made of this other thing which is defined in another file where a bunch of parameters are varying across this population, and then you play all of these in parallel. And then this is defined somewhere else. I don't know where. That's probably here, yeah. And then this, so this is the older syntax. So now this is written in a different syntax. This is what we've been dealing with in the previous months. This is equivalent to the kind of syntax that you've been seeing, it's just different. So this thing itself has a not entirely trivial definition. So now we have a hierarchical composition, that we have a thing which has a non-trivial definition. We give it a name and a bunch of parameters that we're passing to it, and then we drop it into a bigger game. Now, the question is, so what can you do with this kind of thing? So, and the answer is that you do stuff like you loop the equilibrium check over these parameters. So you're kind of, what you actually care about is searching in this parameter space. So you want to find like the minimum, the minimum of this that min-maxes this other one in order to cause this player to fail to want to deviate. So what this actually is this is describing an attack by a briber. So here we're taking the role of a mechanism designer who wants to choose the parameters in order to maximize the cost to the attacker of a successful attack. Where a successful attack is one that disequilibrates everybody else. So you get the kind of thing that we can start to do. So you can start to do things that look like actual, like honest to God economics on top of equilibrium checking if you have a critical amount of complexity. And exploring the extent to which you can push this is an ongoing thing. Like we are not 100% sure how far you can push this. There is one big barrier. The thing which could go horribly wrong. The thing when all you have is an equilibrium checker, the user has to specify the strategy profiles. And this gets harder and harder. I mean, you know how hard this gets. Finding Nash Equilibria is very hard. Finding even remotely plausible things that might be sort of close to a Nash equilibrium is also gets extremely hard. So here we hit the kind of, from a practical perspective, we hit the thing which will cause open games to either fail or succeed, and we don't know which yet. Is what this thing is trying to be, or what we're trying to make it, is a sort of modeling assistant. Our ideal user is basically an economist, and this thing is never intended to replace economists. If you talk to computer scientists doing game theory, they'd say like stupid stuff like, oh, we're doing this better than economists, we're going to automate them away. Like, this is all stupid. The point is to is to automate things that the economist should never be doing in the first place. What this should be is something like a rapid prototyping tool, because so in business as usual in economics right now, when you're doing these models, you basically have two alternatives. If you want to solve a model, either you could try to go to your whiteboard and you could try to solve it on the whiteboard analytically, I mean, typically this gets quite difficult quite quickly. If things get more than about 3 stages, I mean, for extensive form, you end up doing backward induction on like the number of nodes grows exponentially. If things are continuous, you end up getting like more and more differential equations added into your system, and just like things get difficult to solve analytically either way. The alternative is that you hack this up in MATLAB, and then you have a different problem, because MATLAB is not built for game theory. It's not built for economics, really. Economists like to pretend it is, but it isn't. The concepts which MATLAB makes easy are not the kind of true natural concepts of economics. You have to put a square peg in a round hole to make this work. What this is intended to be is a MATLAB killer. This is supposed to be a thing which does the job of going to MATLAB to hack up your model and then solve it computationally, but better. And by better, I mean not faster in computation time, I mean faster in programmer time. And I mean faster in programmer time where your programmer is not like a trained software engineer, but they're an economist struggling with MATLAB. This is the intended use case. This is supposed to be a computational assistant for economists, which is better suited for their needs than MATLAB is. And better still, I mean, I haven't even said Fortran. Fortran is like MATLAB, but even less good. I mean, these are ancient languages.
Question, Jules. So you mentioned mechanism design. I think this is really cool. So, you know, without going to the details, so can you run us how you choose this, how you maximize the objective of the designer with only the equilibrium checker?
Yeah, I might have some examples of this working. I'd have to.
Yeah, but also like just out of your mind, kind of an outline. I don't. Yeah.
Yeah, we do this kind of thing.
Yeah.
So this is now a different model, but closely related one where so here we see. So given some parameter, we find the minimum of another parameter coming from a search space, satisfying this condition where, so this is just saying somebody deviates. So we find, for each parameter, we find the minimum of some other parameter that causes a fixed strategy profile to not be in equilibrium. So this is the point where we're calling the equilibrium checker. And then given this, we can, what do we do? Then we this collects all the values of this into a matrix, and then we min-max it. I think we find the minimum. Oh God, yeah. What's this? So we find the minimum. Oh yeah, we find the min-max of this parameter where we maximize. Yeah, I don't see what's going on. I don't remember. This was like a month ago. And then we moved on to doing something slightly different, and then actually running this takes like 5 minutes on my laptop. And we get out and this thing is a non-trivial optimization problem. This thing has a proper interior solution, which is quite nice. And when you're just messing around with theory and then you just come up with an example, 9 times out of 10 you accidentally end up with boundary solutions, and then things are boring. Yeah. So this is the kind of thing, and the numerics there is super naive, and also Haskell is not a super fast language. that's why economists actually use Fortran. As Fortran does for real go fast. That's something that it is unironically good at. So this is making an intentional, conscious trade-off of computation time for programmer time, because computation time is cheap and programmer time is expensive. I mean, it's better for something to take 2 days to run rather than 5 minutes if you save 2 days of programming time.
I have another question. This is a little bit out of the box, but I was wondering, right? So one of the cool things in machine learning when you use the simple activation functions, right, is the idea of deep learning, that you keep adding this simple stuff and eventually you can approximate complicated stuff. So one thing that we use in econometrics, these are statistics versions of economics, is basically that we would like to have some data on actual strategies played by, say, 2 firms competing, oligopoly, right? So basically, becoming a monopoly price or defecting, right? Kind of prisoner's dilemma, but for prices. And the idea basically is that we like to have, a model, which is what we can do with your tool, right? And then we have to specify a payoff, right? That we don't know, right? So it's going to be known up to a parameter, right? So, and then, we minimize the distance of the likelihood of the actions, conditional on the parameter being forming part of an equilibrium, right? So for this parameter that we're minimizing the distance is constrained to be an equilibrium, right? So that's the use I finally, will see of this, which is, this nice way of writing the model, right, on an oligopoly game, right, and then minimizing this distance. Now, in that regard, I was wondering, so can we use this idea of sequential play to, even if they are not actually playing sequentially, right? Say you have cross-section, but you have a kind of linear game, and then you compose it with another linear game, maybe with this.
Yeah, so I've actually thought about this exact question. And there are very, very good reasons for wanting this to work out. It turns out, so I don't know how to do this. It turns out there's this weird mathematical barrier to doing this that I don't understand, and several different things that I would like to do go wrong for apparently related reasons. Another thing that I would like to do is, so here's something that sounds different, but I also can't do for reasons that I believe are closely related, is that if your action spaces are continuous, what I would like to do is the equilibrium check, instead of returning true or false or this data structure containing deviations, instead returns a dump of Mathematica code. And it generates Mathematica code to solve the system of equations that you need to solve this game. And then, so this is a proper separation of concerns, where open games should be doing the things that open games are good at, and Mathematica should be doing the things that Mathematica is good at, namely solving systems of differential equations. This is a thing I would very much like to do. And another, and so another example, is if everything is linear, or say, so now I mean linear in what mathematicians would call affine. If solving this thing basically becomes linear programming, and then if you can dump the solution of this linear system off to an off-the-shelf linear programming solver, then you can scale this thing just wildly. Then you can have millions of players, completely heterogeneous, and the linear programming solver will probably handle it.
Jules, one thing, so I don't know if you are aware, but for instance, the problem of utility maximization has the same issue, right? So, finding a maximum is NP, so it's complicated, but verifying that something is a maximum is it's polynomial, and we know how to do it. Now, one development in Econ that I don't know if you're aware is this idea of reveal preferences, which is basically a trick to converting, the checking of whether something is a maximum, coming from a utility maximization of some utility without specifying the utility. It converts this into a system of linear equations. by just leveraging the fact that utilities, we assume them they are concave in many situations, right? For instance, with risk aversion. And, you know, by using some convex analysis, it's very old math, but, you know, it's very useful in this setup. You basically write an equivalence theorem that says, if I check the system, so I have choices, right? I have budgets. If I check that this collection, a final collection of choices and budgets satisfies the system of linear equations, then I'm sure this comes from maximizing some utility that is concave.
Okay, yeah. Okay, this is not a thing I've heard the term reveal preferences, but no, this is not a thing that I knew about.
Yeah, so there has been some advances on, I mean, in theory, you can take it, these same ideas, especially to correlate equilibrium, right? And you can make it into linear programs. I'm not, so at least for correlate equilibrium, I'm pretty sure you can do it. I don't know for the general case. But then basically, then you convert this problem of actually solving the game, you know, into checking system of equations.
Yeah.
The trick is because you have finite actions, you can basically think of utility instead of a function, you can think it as a collection of numbers, right? And then this will enter, you know, system of equations, basically the constraints that will make it, you know, be a correlated equilibrium, for instance, right? So it becomes an operator. There exists a collection of utilities, right? But now are numbers because one per each actual action, which is discrete. And well, and short story, this simplifies a lot the computation, right? So this is, and I can actually do it non-parametrically. Yeah.
No, this is not a thing I knew about, but it sounds, yeah, it sounds related to these other problems. So the answer to your original question is, I don't know how to do that. I have specifically thought about it, and I'm highly incentivized to solve this problem. And I intuitively believe it should be possible. I just can't figure out how to do it. Yes. By the way, so while I was looking at this page of code, I realized there's a Hassani type space here, which I promised you an example of earlier. So this, the successful attack payoff is a Hassani type of the attacker, because this is saying how incentivized they are to make, because making the attack is costly to the attacker. So this number, this parameter basically says how incentivized the attacker is to have a successful attack. And then this is drawn from a common knowledge distribution. And this probability, this is one of the exogenous parameters. This is somewhere in this list. And this is saying that with probability 1 minus p, this thing is actually 0, and the attacker has no incentive to be the attacker at all. But the players don't know it. They only have they have a correct prior belief about the probability that the attacker will appear, but they don't know the attacker is there until, and then the timing works out because there's an earlier stage where the players have to commit. They have to make they have to commit stakes to a pool, and then later they get bribed, and then they find out that if they get bribed, everyone else has got bribed, and now they're losing their money. So yeah, so okay. I can say, okay, so this is as much as I wanted to hand wave the, so yeah, the big barrier that we don't know to what extent we can overcome is the problem that I got heavily derailed from this point at some point, I think, is the point that the user has to supply the strategy profile to be tested, and this becomes difficult. The theory doesn't help you with that. This is the thing that doesn't scale. It remains to be seen how much we get away with it, basically. The hope is that in every real case where this is being used, it's being used by some economist who is modeling some situation, and they have some kind of prior conception about how this thing ought to behave. So they have some starting point. This is one of my guiding principles, is that algorithmic game theory, that like equilibrium search, like the kind of the pure study of equilibrium search procedures, is missing an important point, which is that games do not come out of nowhere. they come out of the mind of an economist who is actually trying to model some real world situation. And the economist has some extra knowledge somewhere which is not being encoded in this model. And the question is, how do you get this information? So so equilibrium search is basically saying, we don't care. We're not going to bother trying to extract the knowledge from the economist. We're just going to hit this with a computational hammer. I'm trying to do something a bit more subtle. So I'm trying to work more closely with the economist. That's the idea. But yeah, this is not at all to say that equilibrium search is a useless problem. These should be kind of complementary things. I would very much like to be able to hook this up to partial equilibrium search, where the user says, I believe that these players should probably have these strategies, but I have no idea about the rest. Let's send it to the solver. But this is all, this is all future stuff, and it's what we don't really know is how useful this is going to be in practice. But yeah, the working hypothesis is that this is useful to many people. Of course, we're biased. This hypothesis has to be true for open games to reach their maximum potential.
So, Jules, a quick question. So if it's not very easy to find all the equilibria, is it easier to, given the strategy profile, to find all the payoff values that would generate these strategy profiles in equilibrium?
I hadn't thought about this.
Because like in analysis of empirical games, as Victor were describing them, so we often assume that there is some noise in the utility function. We observe some distribution over profiles that is coming from the data, and then we're trying to match the distribution implied by the model, so by particular specification of payoffs, to the observed distribution over outcomes.
That could be. I hadn't thought about this, but that.
And often what people do, they draw some random payoffs. Yeah, so payoffs distributed according with respect, so they have some parameter. You fix a parameter, draw random payoffs, then solve the game. And then you just start doing it many, like 100,000 times. And then you compare the distance between the observed distribution and simulated distribution. And then you just try to minimize that thing. And then you find the parameter value that then minimize this thing. But instead of maybe drawing these many times, I'm just saying, okay, so for relatively small games, I can fix the profile and find all the payoff values when this profile is actually in equilibrium. And in a sense, this might save me lots of time. Instead of solving the game and given the payoffs, I find the strategy profile, can fix the profile, because all these games usually have like full support of payoffs. Payoffs can take all possible values. And then almost any payoff might, I would say, almost any strategy profile might be an equilibrium for some payoffs. And then the question is how to kind of aggregate, like how to integrate out this unobserved noise.
This sounds like it could be something that open games can help with. I guess by help, I mean, again, the code might factor through this kind of structure so that there's less code to write. And that the code is closer to the true concepts, perhaps. Yeah, hard to say for sure when I've just had the idea for the first time, of course, but yeah, okay, interesting. I would like to say a little bit about the link to machine learning here. So I don't have any code to show you for that. So the story there is, so I've told you like a long time ago that open games are a big overgeneralization of game theory. And in the early days, like 6 years ago, how I explained this was just like, we take games, we close under compositionality, and then mathematically this other junk appears, and then we ignore it. now I have a much better understanding of what else is out there, and a lot of it is not junk. And quite a lot of this space actually is taken up by various forms of machine learning. There are two different links between open games and machine learning, which, yeah, the fact that there's two different links is weirdly suspicious, and this has led me on a whole new research direction trying to understand why this is. So one is that is linking to backpropagation, and then the idea is that the way that the forwards and backwards information flow in an open game interact with each other turns out to be basically exactly the same as how the forwards pass and the backwards pass interact with each other in backpropagation. So that's the first miracle. So what it seems that you can do is that you can, so we haven't actually tested this, so take this with a pinch of salt, but this is what I believe is true, is you can replace your argmax players with basically gradient-based maximizers. And then all of your backwards pass, instead of passing back utilities, you're only passing back gradients, gradient covectors. And then this thing is like literally backprop, I think, in the sense that as far as I can tell, you could literally do this in terms of, like you could do this with like TensorFlow. Figuring out what to do with this knowledge is going to be fun. The other link is to reinforcement learning. Because so actually there's a more direct link to dynamic programming, and so what you end up getting, so so taking a step backwards in a different direction, the study of figuring out how all these things relate to each other, I have named this field categorical cybernetics, because cybernetics is a historically discredited word which turns out to be a good description for all of the things that seem to be hit by this. It's like, what is the least common denominator of like control theory, machine learning, game theory? Cybernetics is quite a good label for this. So the way in which Bellman value iteration works turns out to be structurally the same thing again. What I think we are repeatedly discovering is things which are folklore. I don't believe we've discovered anything new anywhere here. I think all of this is folklore, that individual people kind of pairwise knew that these things are kind of basically the same thing. But somehow and I think I credit category theory for this, that category theory has given me the high level viewpoint to actually see all of these at the same time. And I think I have an idea what's going on, but yeah, this is a whole new research direction. The Bellman value iterator, that is to say, the thing which you apply to the value function to do one step of value function iteration, is structurally basically the same as one single step of backpropagation through a neural network layer. And it's also the same as how you do kind of one step of backpropagating in an open game, these counterfactuals. Like backwards reasoning, one step across a box which is facing backwards. All these things relate. So in this very exciting situation of like, there's all these questions, and I believe none of it is exactly new, and it's going to be a massive headache to try and publish this, because like for every individual thing, there's going to be someone that says, oh yeah, we knew this in the 60s. The practical side of it is that all of these things, and actually, by the way, another one is you get one from Bayesian updating. If you have, this is a really cool fact. There's a sort of chain rule for Bayesian updates, where if you have a stochastic, so if you have a stochastic function, so given an x, return a y stochastically, and you have a prior distribution on the input and an observation of the output, you can get a posterior on the input. And if you have a stochastic observation of the output, you can linearly extend this. So if you have a prior on the input and then you have a kind of stochastic observation of the output, you can get a posterior. If you have a sequence of two of these things, of like the output of the first stochastic function becomes the input of the second stochastic function, and you have a prior on the input, and then you have an observation of the output, it's just backprop again. It's another instance of the same pattern, which means that you can do some kind of Bayesian estimation using open games, I think. But again, this is a thing that we kind of think for theoretical reasons that this is possible, but haven't started looking into it yet. So the practical upshot of this is, even though I believe that none of this is kind of new science in the sense that all of this was folklore to somebody, what we get is that all of these things are things which can be done in the Open Games code base. These are all things that can kind of fit in what this tool can do. And the really exciting part will be actually combining them. And I'm now degenerating into kind of wild speculation, but it's kind of reasonable to expect that you can do hybrids of these things. So the very first thing we're doing, and this is the one thing that we're doing first, is multi-agent reinforcement learning. So that is to say, we're combining the reinforcement learning aspect with the game theory aspect. So me and Philip Zahn are just starting to work on this. And actually, he's doing most of the programming because he's the economist. He's a microeconomist, so he's a much better programmer than me, obviously. So he's actually writing this like Q-learning in Haskell and stuff. None of that code's available yet, I think, or maybe it is, and I'm not sure where it is. It's on a fork of the main code base. Yes. I guess that's probably everything I wanted to say about machine learning, which is to say a lot of crazy ideas that will be things that happen in the future. And again, we're not sure how practical this will be or how useful it will be or even how new it will be. Eventually it becomes new just from the fact that you can do it all in one place, which has definitely not been done before. I guess the hypothesis is that a language like this, and this language was built for game theory, but I think the abstractions that it provides are the right abstraction to kind of do all these different things in one place. There's a whole separate issue whether Haskell goes fast enough, but that's a problem for a slightly later time. Initial results are it probably goes fast enough for at least toy examples with like thousands of parameters rather than millions of parameters or something like this. Yeah. Okay, so I guess I've allowed myself to overrun because I didn't have a fixed stopping time. But I'm now trailing off into wild speculation, so I should probably cut myself off. Hopefully this, yeah. I guess that's the end. Hopefully this gives you some. I try to give kind of all of the different aspects from the theory to the really practical side and things in between and crazy future things. And
thank you so much, Jules. I want to have one more question because this is very interesting.
Yeah.
So there is, I have seen some work on category theory and game theory besides your work, which is basically trying to find, and you have already this definition when you gave us the canonical representation of a game as a string diagram.
Mm-hmm.
So the notion of equivalence, right? You also have this section on your paper. So mm-hmm. Two games are equivalent if they have the same string diagram.
Yeah, and actually this is a little bit sketchy. I suspect the question of equivalence of games is actually a really deep theoretical topic.
Yes. Yeah, so I want to ask you, you know, I understand this is more complex also from I'm not a specialist on that, but, you know, I think one useful thing about this equivalence is that I have seen some recent applications to information design and mechanism design where, you know, solving over the whole domain of games, you know, is very complex, but if you find the quotient space, then it becomes actually simpler, right? So there is, especially when things are dynamic and sequential, right? So basically what you do is you find, you know, the quotient space where there is a canonical representation, which is easier, right? So all these crazy games map to this simpler object. And now we can solve our mechanism design, information design problem there in the quotient space, which reminds me a little bit of this idea, but I don't know what are your thoughts.
Yeah. Yes. This is something which I think open games can say something about, but the mathematics gets really difficult. Because so the thing is that you need to talk about maps between. So for this, you need to talk about maps between games. But the thing is that open games are already a kind of map between their boundaries. So now you're in a two-dimensional situation. So you have like boundaries, and then you have open games between boundaries, and then you have some kind of maps between open games. And so now you're doing two-category theory. And the thing about two-category theory is that it's really, really difficult technically. It makes my head hurt. So I believe that there's stuff to be said there. I'm not sure how much stuff. So the thing is that you can talk about kind of maps between ordinary games, things like quotients, like subgames quotients, like product games. You can talk about all this kind of stuff. These are just ordinary, like say, either extensive form or some kind of ad hoc foundation designed to make your life easier on this. When your games are also open, then your life gets difficult, because then you have to worry about there's just too many different ways that things can interact, because now you have like, because open games are already sort of two-dimensional objects. The syntax being two-dimensional is not a coincidence. There is some kind of, and this is getting into like proper category theory now, but there is something kind of inherently two-dimensional about open games. So adding maps between games makes these things three-dimensional, and 3 dimensions is hard. In the sense that you get into kind of topology, and kind of the topology of what can happen in 3 dimensions is really complicated. When you take the category theory seriously, you end up in these kind of issues. So it might possibly be more effort than it's worth to use these kind of tools to ask these kind of questions. On the other hand, there might be some really, in fact, there probably is some really cool stuff there. It's just, it's really difficult to understand. And if you talk about, so one of the things which I kind of observed could be there and then ran away screaming because it looks so difficult is to say, there are such things as homotopies between Nash equilibria, where you take seriously the fact that your strategy space is not just a set, it's a simplex, it carries a whole bunch of topological structure. And you can talk about homotopies inside this space, like continuous deformations. And this, once you hear this idea and you know a bit of category theory, this causes you to run away screaming, because homotopy theory is a straight line to like infinite dimensional stuff. So there's probably some stuff to say there, but I'm not going to be the one to say it, I think, in that case.
Thank you so much, Jules. So I don't know if the students have any other questions, and because I know you plan around 2 hours, so my students mostly, but I'm free to you have some more time if you.
Yeah, no, I have nothing else to do today, so I can.
Cool. Yeah, so I think a lot of people are very interested about what they're doing. Of course, the idea of this class is to generate ideas, right? So for future dissertations, I don't know if any one of my students is going to be interested, but for sure there is a lot of excitement. I think this is really cool. Personally, I enjoy it a lot. So
another thing that I care about, and this is a purely non-technical thing, I haven't talked about it, but maybe you can just guess from my background, is I care about the social aspect of getting different subjects to talk to each other. I think we lose a lot by academic siloing. I kind of wish everybody was just mixed up together in one big happy department. And so I'm already coming from 2 different directions, from theoretical computer science and mathematics, which at least are quite close together, whereas economics is kind of different. And there's kind of bad blood both ways. Academic economics as a whole has a terrible reputation, probably deserved. The fact that this class exists gives me a lot of hope for the future, let's say. I hope there are classes like this all over the world happening. If not, then it's just you against the rest of the world. So good luck with that. I think for sure, computer science, like abstract mathematics, has a lot to give economics, but it goes both ways, because just as an economist is likely to say, computer science is a waste of time, we don't need that, like Fortran is for all we need. Like we had this in the 50s and it's fine. You're equally likely to hear a computer scientist say, economics is all bullshit, there's nothing there, just ignore it and do like, we know how to do game theory. And they're equally stupid. So this is part of my thing. I have to fight both sides, of course. This doesn't make me a lot of friends.
You're right about econ. Econ is a very weird field, but there is a lot of people working in econ because by nature is very multidimensional. So that's the cool thing. I think there's a lot of people that still care about innovation. So I think we're happy to hear this new stuff, right? I think this is very exciting, because I think one big barrier for game theory is actually the language, right? So which we try to abstract it as a simple interaction, but there is a lot of internal games, right? And I think this analogy that you made to machine learning is great, because I think creating this idea of even trying to model some observed simple actions as a deep game, right, with a lot of potential hidden interactions that we don't see, is very powerful, I think, empirically. So I was telling you that I think Western has this mix of theory-minded people, like mechanism designer, information design, but also structural people. So for me, it's just exciting to try to think how to bring this to an estimation problem, right? So as Nail was describing, the minimization, of a distance, of a likelihood of observed actions versus, this model as described by this tool in this particular case, right? And trying to explore the potential there, so which seems very exciting. So students, feel free to ask any other questions.
I have some questions. The first one is about the iteration you talked about. Function iteration.
I never talked about repeated games or Markov games or anything like this.
Yeah, I mean, have you considered evolutional game?
Evolutionary game theory is one of the things that I don't know how to handle.
Okay.
Evolutionary stable strategies is one of the, this is in the space of solution concepts that I don't know how to deal with. There is, I guess, some reason to believe it should be possible, but I'm not really sure. Okay, yeah. Now I've just been reminded that repeated games of any kind exist.
Yeah.
So all of the things that you saw were basically single shot games. They're a thing where every play terminates after a finite time, and then any kind of iteration is happening on the outside, like you're looping over an update or something like that. Infinitely repeated games we can handle, and there's a paper by some people who don't include me, which is theoretically quite nice, but I have never been able to figure out how to implement it on a computer. But in theory, like this is a case where in theory we can handle repeated games. In practice, there are computational issues. You end up taking like argmax over something that's like too big to search. It's like take argmax over infinite objects, and which mathematically is fine.
Okay.
Markov games is a much better situation because the dynamic, what I said about dynamic programming could be said in a different way, and this can be formulated directly in terms of a formulation of Markov games. So I'm not quite sure why Markov games are easier to handle than repeated games, because the rest of the time, imperfect recall makes all kinds of things go horribly wrong. But somehow adding imperfect recall to repeated games makes things work, and I don't understand why. No, but yeah, evolutionary games is not a thing that we figured out, but I've never really spent serious time. Yeah, you get the idea. There's I mean, pulled in a million directions, and some things are higher priority than others. So
the other things that you talked about, finite belief. I mean, finite order belief. I mean,
yeah.
Generally, it's when the belief order goes to infinity to become common knowledge. So have you considered in this way?
Yeah, I might have said something false earlier. So the situation that we can handle is the situation where all beliefs are correct. So but then you can encode, like you can encode false beliefs using the Hassani trick, as long as they're finite, I guess. I'm a bit sketchy on this. I'm not exactly confident in what I'm saying here, so this might be wrong. Common knowledge we get by default anyway without having to encode it.
Okay.
So that's okay, but it's not. We can't make it explicit. It's kind of implicitly there that the entire structure of the game is common knowledge. That's why we get the correct beliefs thing, because the strategies, when you do an equilibrium check, the strategy profile ends up being common knowledge.
Okay.
So that ends up with the prior ends up just being a copy of, so my strategy ends up being my prior ends up being a copy of your strategy, yeah.
And another question is, you talk about mixed strategy. It's hard for your language. So have you considered behavior strategy?
Yeah, behavioral strategies is what we do. So
yeah.
with the Bayesian open games, we use behavioral strategies.
So it's easier. Yeah.
It fits the category theory better, funnily enough. Okay. This is really the reason that I never considered mixed strategies in the first place very much, because the category theory told me that behavioral strategies are the right thing to do. But then this leads to what this is, I guess, one of the reasons that perfect recall is a very important assumption, because that's the thing that says that it doesn't matter how I do it and you get the same answer. Yeah, the other reason is that I end up heavily abusing one deviation at some point. So
okay, the last question is, there is a result in games. It's like it's by Wilson, 1971. It's kind of like a game with a finite strategy space. It will has the number of the game, the number of the equilibrium of a game with finite strategy space is odd.
yeah.
So
that's a consequence of Brouwer's theorem, right? Brouwer's theorem says that you have an odd number of fixed points.
Yeah. And so can you handle the questions like this? I mean, the language?
I don't think so, no.
Okay.
This not. I mean, maybe, but this kind of thing is not fitting into the category theory very well. One of my life goals is to understand a result called the Lefschatz fixed point theorem, which is a heavily upgraded version of the Brouwer fixed point theorem, where you actually get an explicit formula for the number of fixed points in terms of like homology classes. Like this is like historically led to a whole field of pure maths and like algebraic topology and stuff. And one of my life goals is to understand this. And it's conceivable that this could link together, possibly.
I consider this question is kind of like when I was reading a paper, I think it's kind of it's linking the group theory and some ring theory. I mean the algebra group theory, and so, yeah. And
I mean, so
I think it's like maybe your theory is not helping solving it's like maybe group theory is not helping solving a polynomial equation.
Yeah.
But once it goes to Albert impossible theorem, then it needs that part. So maybe your language is not good at dealing with the computation, but it can deal with the boundary of some questions.
Yeah. Yes.
It falls on parts.
It's conceivable. I think maybe what you noticed is that category theory is itself a sort of algebra. Like categories are kind of like groups and rings. The main difference is that groups and rings have inverses of things, whereas categories do not.
Does not have invert.
And there is a version of like categories with inverses, and that's called a groupoid. So yeah, groupoids are like a cross between groups and categories, or they're like the least common generalization.
Yeah. Just
this kind of hits on that. There's a kind of deep irony of open games, which is open games are extremely heavily theoretical.
Yes, so that's what I'm asking this part.
But they seem to not be useful for theory. They don't seem to be useful for doing theory. What they seem to be useful for is kind of the practical side of game theory.
Okay.
This is I love this irony. I enjoy this irony. It's because it makes everybody uncomfortable. It makes the theorists uncomfortable because they have to think about practical things. It makes the practical people uncomfortable because they have to think about the theory. Nobody is entirely happy except for me. Open games have never appeared to be useful for doing any kind of theory with games.
Okay.
It could be just I've been looking in the wrong place. The analogy is something like the theory of programming languages is, no, hang on, how do I want to say this? There should be an analogous fact about programming language design, I think. Like designing a programming language is not useful for thinking about the nature of computation itself. It's useful for just writing programs. Something like that. Whereas the theory of computation is a field, like is a big field, but they don't really need, they don't use anything about programming language theory. They're basically disjoint. So yeah, in that sense, open games are like programming language theory, that it's deeply theoretical, but motivated by practical things, I think. Yeah, that sounds like a sentence I could convert into a tweet. Yeah. Okay.
Yes. So any other questions? Okay. So thank you so much, Jules. It was super fun. So we enjoyed it a lot, and definitely let's keep in touch. I think I want to marinate some ideas, and let's talk at some point. But also, I encourage all the students to to keep learning about these tools in category theory, and the open games in particular. They seem to be really useful and really cool. There is all these connections of machine learning, backpropagation, dynamic programming, games, which I think are super powerful, especially for us that are structural. Imagine if we could do some backpropagation in a proper large game. That would be amazing, right? Yeah, so I think that's pretty cool.
You can contact me. Like, you can find my email on my website, I guess.
Yes.
I'm not extremely fast at responding to emails, but I'll get there eventually. And I will put this on YouTube. I think this went well enough that I'll put it on YouTube, unless anybody is unhappy. If you're unhappy, it's completely fine. Let me know. If nobody lets me know, I think I'll put it on YouTube probably.
I'm fine. You can also, or nay or yay. Okay, cool. Okay, thank you, Jules. And definitely keep going. We're gonna check. I never done Haskell, but you got me interested. I'm playing with Julia recently, which is more Fortran-like, but definitely seems like a fun thing to do.
And Julia, right? And Julia is also another language that I am also interested in, and we strongly considered to rewrite the entire code base into Julia.
That one is fast. So, for instance, that will be easier for structural people.
So Julia is also positioning itself as a MATLAB killer, but for general purpose, and even more as a Fortran killer, but for general purpose numerics. Julia is a very, very nice looking language, and there is a library in Julia called catlab.jl, and I know quite a lot of the developers, and it's a category theory library, and it includes string diagrams. It has string diagrams in this library, and this is like already vastly better than anything that Haskell supports.
Oh wow!
Even though Haskell was supposed to be designed around category theoretic principles. So.
Catlab, okay. I'm sure to check it out. Yeah, I think the only thing, I don't know if you have seen NetLogo with agent-based models. I mean, that's the closer I got into anything more.
Yeah, no, this I haven't.
But I think
at least I've heard of it.
Yeah, but I mean, that's the only kind of semi-close thing. But yeah, I definitely gonna check Haskell.
Yeah, I mean, it's for sure it's related to Gambit.
Yeah.
The MATLAB library for games. I mean, anything that anything isn't right. A lot of what you could do with the Open Game Engine could be done with Gambit, and Gambit also has equilibrium search, which is its main reason to exist, I guess. But yeah, I guess the point of the Open Game Engine is to do all of the stuff other than equilibrium search better than Gambit does it.
Okay.
You wouldn't want to. I guess you wouldn't want to do agent-based modeling in Gambit, whereas you could do potentially agent-based modeling in the Open Game Engine one day.
Yeah. The connection with the dynamic programming is this, if I'm correct, is the length mapping, right? So which allows you to have this passing forward and then backward.
Yeah. Oh yeah, right. I've spent like 2.5 hours avoiding saying the word lens. And I just kind of remembered I could have done this all along because you read the paper. Yeah. So yes, the common abstraction of all of these things that look like a forwards pass and a backwards pass, this is lenses. So this is this is my working hypothesis on this kind of categorical cybernetics direction, is that lenses are the right mathematical abstraction for all of these things. It's a thing which can be used to pin down these kind of vague intuitions that many people have that these things kind of look like each other.
Yep.
You can kind of pin it down mathematically that they look like each other because they're both examples of lenses.
That seems really powerful. I like that a lot. I think eventually, as you mentioned in the differentiable case, maybe there is some nice, equation like what we have in econ, the dynamic programming, what we call the Euler's equation, which is this, gradient based, that how you pass from t to t+1, right? But for games, right? So how you pass from some action to some player plan. I think these equations, even if they don't solve the game, they provide a lot of intuition, right? Especially for economists, because you have this idea of how these things interact and propagate.
Yeah. Now I should think about the question like, what is the analogies of Euler's equation in all of these other examples? That's I don't actually remember what the Euler equation is. I'd have to look this up. That's a fun question.
That's basically the gradient of the basically of the view function, right? Related to the update through the expectation operator. Yeah.
Oh, okay. Yeah, that's the thing I should look into. That's for sure.
Okay, so thank you so much, Jules. It was fun. We enjoyed it a lot. So we thank you.
Thanks. Yeah. Okay. Bye.